Okay, so now when we know how to derive individual private and public keys from the root key, let's talk about how we convert these public keys into the addresses. So Bitcoin addresses are nothing else but a human readable representation of the Bitcoin script. So Bitcoin has a nice scripting language that allows us to define the spending conditions for our Bitcoin. So when we have, for example, the Bitcoin transaction, what we have a certain number of inputs, certain number of outputs, and every output defines the script. It is called script pubkey. That is defining the spending condition. And then when we want to spend this output, we need to provide, so the next transaction that has an input that is spending this output, it contains the script sig, basically a set of elements that will make this script to evaluate correctly. So this is normally the public key and the signature in case of the pay-to-pubkey hash, but for multi-sig it will be a set of public keys and signatures, or maybe I think just a set of signatures. And for more complicated scripts, there should be other elements on stack as well. Okay, so let's look at common addresses. So there are like three common types, addresses types that are used for a single key transactions. So first, the legacy addresses. This is what we had before the Segwit. So this is a pay-to-pubkey hash. Then there is a native Segwit, and it is pay-to-witness pubkey hash. So the only difference is that these elements that are in the transaction input, they will be not in the script sig, but instead they will be in the witness. Okay, and then we have the nested Segwit. That is a hack to make, well, basically to do the backward compatibility with legacy software that doesn't support Segwit. And here we use for legacy addresses and nested Segwit addresses the base 58 encoding, so these characters, and then in native Segwit we use base 32. Because it is a little bit better in sense of displaying as a QR codes, because in Bitcoin we normally display addresses and other stuff as QR codes, and this character set is better optimized for QR code encoding. Okay, so what do we have in the nested Segwit? We basically have our normal pay-to-witness pubkey hash, and we put it inside the pay-to-script hash thing. So then we still have a backward compatibility with legacy software, so any software wallet will be able to scan this address and pay to it. Okay, so let's take an example of pay-to-pubkey hash, how exactly this works. I will, let's see, so the script itself basically has the following structure. So we have the opcodes, the operators that do stuff. And the script for pay-to-pubkey hash is op-dup, duplicate the element, then op hash 160, hash it. So hash 160 again is the repmd D160 of SHA-256 of, in this case, it will be the pubkey. Okay, then we have actually the 20 bytes long pubkey hash. And then we have two more operators. So first we will be op equal verify, and then op checksig. So what happens then is when we have the public key and the signature in our input of the next transaction, we follow this these opcodes and do the following. So op-dup will take the first element and duplicate it. So we will have again another public key in the stack. Then op hash 160 will apply the hash 160 function to this public key. So instead of the public key, we already have the hash of public key. Then we have another element that is the pubkey hash that the sender defined. And then op equal verify will compare this value that we have in the output with the value that we have in the stack right now. So basically it will compare if the public key that is provided in the script sig is actually is hashed to the value that is defined in the script. Okay, so then we will get rid of this and we will go up to here, yeah. And then we have op_checksig that basically verifies the signature against the public key. So we have here already the public key and we verified that it is the correct public key. And then we have the signature. So if the signature is correct for this public key, for this transaction, then everything is fine. The script is satisfied, so we can spend the Bitcoin, so the transaction is valid. Yeah, so then the native Segwit script is actually way smaller, so it is just 00, the version of the Segwit, and then the hash 160 of the public key. And when our software wallet sees the script like this, he understands that, okay, this is the pay to witness pubkey hash, so I know what to do next. So it's just made just for simplicity. We don't need all these opcodes anymore. We just provide the 20 byte value and the version of the Segwit, and we know what script to evaluate. So then basically as soon as the software detects this kind of scripts, it goes and evaluates this script there. And then the nested Segwit, it is basically taking the hash of this script and puts it into the standard beta script hash. It is one of the BIP 16 maybe, I don't remember exactly, but you can look it up. So basically it defines the way how we can pay to complicated scripts without the knowledge of the full script. So the receiver just gives us the hash of the script and we pay to this script hash. Okay, so let's see how they are encoded. So the legacy addresses, basically what we have, well, we have it in all addresses actually. So we have the prefix always, so there are different prefixes. So this is the prefix that is dependent on the network to avoid mistakes such that we don't send Bitcoins on the mainnet when we were requested to send it on the testnet. And basically these prefixes are also defining the type of how the rest of the data should be treated. So for example, here we have the pay to pubkey hash prefix. So we understand for the mainnet. So we know that the next 20 bytes from the address we should treat as a hash of the public key and then construct the corresponding pay to pubkey hash script. Then in nested Segwit we again have the prefix that is a pay to witness, just pay to witness stuff. So native Segwit, and then we have the Segwit version here, the Q, it is basically version 0, and then depending on the length of the rest of the address, we have either 20 bytes, then it corresponds to pay to witness pubkey hash, and if we have 32 bytes, then this corresponds to pay to witness script hash. Okay, and in the nested Segwit the same applies. So we have the prefix that is pay to script hash for the main network or for the testnet, and then we have another 20 bytes that are the hash of the script. So in this case we will have let's just have a look at it. How exactly it looks, what it looks like. So let's here in the Jupyter I have already the small notebook that imports everything, and we just need script here. And also I have the seed that we generated from the last part, and also the account and the master public key, and also I derived the single public key here. So then if I want to generate the script that is pay to pubkey hash, Then I take the script, and in the script file we have a bunch of helpers that generate different script types. So this is pay to pubkey hash, pay to script hash, pay to witness pubkey hash, and so on and so forth. Also, we have the multisig here. Then, if we generate the corresponding script and print it, we see something like this. And here we can look up the corresponding opcodes. So, for example, 76 means 76 opt-up. Yeah, so this is a very nice table of all possible opcodes. It is in Bitcoin Wiki. And here we can look up all the values for the opcodes. So basically here 76 means opt-up, then A9 means op-hash 160, then 14 it is a hex representation of 20, so this means that the next 20 bytes is a certain value. So then we have 20 bytes, and then we have two more opcodes. 88 is op equal verify, and then AC is op checksig. So this is the pay to pubkey hash of the public key. And now if we want to display the corresponding address, we just do the script address, and we can provide the network, or by default I already said here that the network should be a testnet. But yeah, it doesn't take it here, so then network equal to networks test. And this is our legacy pay to pubkey hash address for the testnet. Well, for the mainnet, it starts with 1. Yeah. Now let's look at another script, and let's take not a pay to pubkey hash, but pay to witness pubkey hash. So pay to witness pubkey hash script, as I said, starts with 00. This is the Segwit version, and then again 14. That is like the length of the next field, so 20 bytes, and then we have 20 bytes and nothing else. And the corresponding address starts with BC1, so it is batch 32 encoded string. Great. Now let's have a look at another script. Let's take, so if we want to generate the nested Segwit address, we need to convert this native Segwit script and wrap it into, into the script hash. So what we do script pay to script hash, so it will be script 2, pay to script hash, and we provide as an argument our script that is pay to witness pubkey hash. And then again, let's print the value here, and script 2. Yeah, and then let's print the address of this script 2. So it starts with 3. This is a standard pay to script hash addresses. So now let's have a look what exactly is the data here. So we have A9. So let's look for A9. This is op hash 160. Then we have 14. This is the length. So then we have a hash 160 of the script. And we can verify it by just from Bitcoin hashes import hash 160 and then print xlify hash 160 of the script data. So this is the value of the hash of our pay to witness pubkey hash script, and we see that here it is. So this is basically the hash of the script, and then we have 87 that is op equal. So then we have op equal. So this means that our script will ask us to provide with a certain data that is hashed to this value. So if our stack is just a script, then it will hash the script, and then it will compare it with this hash, and then it will go to op equal. But then the logic inside the software will actually understand that, okay, it looks like a pay to script hash, so I need now to evaluate the script. And then we will again have already the script that we hashed here, and then the rest of the stack that will be probably the pubkey and the signature. Yeah, so it is not very straightforward. I do recommend you looking into the BIP. Let's have a look. BIP pay to script hash. Yeah, this is the BIP 16. So it defines how exactly we should deal with the scripts. So yeah, look at it. Okay, now when we have all the addresses for the single key, let's quickly look at the multi-signature script. So what we can do, we can take a bunch of public keys. So let's do pub keys equal to, how did I generate the pub key here? I just derived it from the xpub. And then I will put here I for I in range, let's say 3. And then let's print pub keys. So we have 3 public keys now, and let's generate 2 of 3 multi-signature address. So what we do, we take our multisig, it takes m, and then pub keys. So we do script msig equal to script multisig. We need 2, and we provide the pub keys. And then let's print actually 5 of msig data. This is the thing, the multi-signature script. So the only thing here is that our public keys are not sorted. So this means that the order of the public keys matters. And it is not that great, because then if we generate it with a different order of master public keys of the cosigners, then we can end up with different addresses depending on the order. So there was another BIP that was suggested that we should sort them. So what we can do, we can just put sorted pub keys, and let's print them as well, sorted pub keys, and then it will be sorted hexagraphically. So like the 02 starts first, and then so on. So we can pass sorted array to the multisig script, and then it will be according to the standard. So let's see what it looks like. This is the whole script. And if you just try to do msig address, it will fail. This script type doesn't have an address representation. Because how we do the multi-signature, we have this large script, but then we want to do the script hash of it. So we can do either script pay to witness script hash of this multisig, and then get the address, then we will get an address. Or we can do pay to script hash of multisig, and then we will get the legacy multisig address. Okay, so this is the only thing that you need to do aside from generating the multisig script directly. And then the multi-signature script, let's see how exactly what it looks like. So 52, and here 52. So 52 is basically just op2. So this defines that we want 2 signatures to be correct. Then we have 21. This is basically 33. This is the length. And then the next one will be our public key. Yeah, so then after 21 we have our first public key, then another 21 and the next public key, and then another 21 and the next public key. So then we have pubkey 1, pubkey 2, pubkey 3, and then we have 53. 53 is like by 1 more than 52, so this is basically mean op 3, so it means that 2 of 3 multi-signature, right? And then we have AE, it's op-check multisig. Okay, so basically we here defined, we want 2 of 3 multi-signature, and here is the set of the public keys that we are using. So yeah, this is the multi-signature script. Okay, so I suppose we now know how roughly addresses work. And let's continue and go to some initial GUI programming.